before going into the first speaker, we would like to thank our sponsors once again. So this brings me the pleasure of introducing the first presentation is a keynote on TOPCon R&D developments updates given by Andreas Wolf, head of Group Silicon Solar Cells at Fraunhofer ISE. Andreas, the floor is yours.
Thank you. Can you activate my video?
Yes. Udaya?
Now it should work.
Yes, we can see.
Okay, thank you. So let me start my sharing my screen. So now you should see the Can you now see the screen and my mouse?
Yes.
Great, thank you. Thank you for the introduction and welcome to this update on TOPCon R&D status and development. I'll shortly introduce Fraunhofer ISE. It's the largest solar energy research institute in Europe with a staff of around 1,500 people. And of course, we work on photovoltaics, but we also work on other renewable energy topics like power grids, energy storage with batteries, hydrogen technology, system integration. But today the focus is on photovoltaics, and here we address the whole value chain, starting from ingot on wafer production, solar cell technology, module technology. We have a large facility labs where we have tools, mostly automated, and most of them also ready for larger wafer formats. And we also have the CalLab facilities, which do accredited measurements and give us a good support here. And with this background, we offer feasibility studies. We also provide assistance when generating concepts and basic engineering for setting up new facilities. We offer training and ramp-up support, and we also support during operation with, for example, test lab PV modules. So today the topic is tunnel oxide passivating contact. What's behind this? Tunnel oxide passivating contact is a carrier selective contact, and carrier selectivity meaning that you can extract the majority carriers easily through this contact, while the minority carriers are rejected. And this is realized by the structure that you see here. And you have a silicon wafer, N-type doped usually, and you have a tunnel oxide layer, and the majority carriers can pass through this tunnel oxide by tunneling into the polycrystalline layer on the other side, while the interface is very well passivated by this oxide layer with low defects, which gives a low recombination parameter, and this gives the selectivity, which is key to reach high efficiencies in devices. And usually the fabrication of the structure consists of these 4 steps. You first grow the interface oxide, then you deposit the silicon layer, which might be either doped already or undoped. In the subsequent step, the layer is crystallized, dopant is activated, or it's provided if the layer was deposited undoped. And finally, a very important step is providing hydrogen to the whole system to passivate any main remaining defects. Now, this technology has been around for quite a while. It was known in the semiconductor industry as silicon insulator silicon. It was suggested to be used in solar cells quite early in the 1980s by Martin Green, among others. And it was very likely implemented in SunPower's Generation 3 back contact solar cells. And then in 2013, Frank Feldmann from Fraunhofer ISE introduced this hybrid cell structure with a TOPCon full area contact on the rear side and a boron diffused front junction. And in this publication, we also coined the term TOPCon. And just a few years later, this concept was picked up by industry and industrialization started with Jollywood and LG among the first to go the path of industrial implementation. You can find details of this story and also more details on the TOPCon route in this nice overview paper from Stefan Glunz. Now looking at the industrial cell process and structure here, I brought a generic process flow and cell structure to introduce all you to this process sequence. Most of you are familiar with this, but we go through the sequence quite fast. You start with an N-type wafer, which in the first step is texturized. Then a boron diffusion forms the P+ emitter, and the borosilicate glass still remains on the surface, and you have some wraparound in this process which needs to be removed. And this is done in the next step in chemical edge isolation. I will share some details on this soon. And this process also planarizes the rear side. Then the TOPCon system is formed by tunnel oxide growth and silicon layer deposition, as discussed previously, might be doped or undoped, and in a subsequent step, the annealing is performed or the phosphorus is provided to the undoped layer. This usually occurs with a wraparound as well. Might also be that the whole front side is covered by the layer, so you need to remove this wraparound in another wet chemical step. That also removes the BSG layer. And then next step is the surface passivation. Usually front side is passivated by ALD aluminum oxide and silicon nitride or silicon oxynitride stack systems. On the rear side also silicon nitride based stack systems used. In some cases you also have aluminum oxide on the rear side depending on the deposition technology that's implemented. And for the metallization, screen printing is state of the art. Meanwhile, you use silver paste without any aluminum content anymore due to the LECO technology. Printing is done in 2 steps per side, usually with floating bus bars or even latest developments with a zero bus bar approach. Then contact firing forms the contacts. After this, usually a post anneal is performed, which with the temperature and illumination, which facilitates the hydrogen diffusion into the bulk and increases fill factor and VOC. And finally, laser enhanced contact optimization was one of the key developments in the past years that changed the process. I will come with some details later. So this is the final structure. Now let's look into some details of the sequence. For these 2 wet chemical steps, a cluster process has been established also by our industry partner RENA. And this approach consists of first single side oxide removal step where you in an inline process remove oxide on one side of the wafer and the water cap protects the other side, and this then facilitates the use of a high throughput batch process to etch the rear side, and this gives you the possibility to use industrial tools with a high throughput to to provide cost-effective wraparound removal in these 2 process steps. The TOPCon system formation is also worth taking a more close look. There are different options in the market to do this. One widespread option is the what we call ex situ doping route, where you grow a thermal oxide in a tube furnace, and then an LPCVD process deposits undoped silicon layer, which is subsequently in a second process doped by a POCl3 diffusion. But there are also in situ doping approaches out there. For example, in a PCVD reactor, where you first use a plasma oxidation to form the interface oxide and then can deposit a phosphorus doped layer by PCVD, which is then crystallized in subsequent annealing step. And the same can be done by a PVD approach with a PVD oxide and a sputtering of the doped silicon layer. And in recent progress here is also that you don't use any single layers anymore, but multi-layers that are deposited with intermediate oxide layers to decouple surface properties of contact and interface oxide. Regarding the PVD technology, we do some developments with our industry partners. It's one essential part is to get a uniform oxide thickness of the interface oxide through your industrial process. And this is here you see the oxide thickness relative to the deposition width of the sputtering system, and here we achieved a quite uniform result over the whole width of the sputtering system, showing that there's an industrial feasible process. When depositing the doped silicon layer by sputtering, it is also possible to achieve very high implied VOC values, like you can see from this publication. Up to 740 millivolts were achieved. And this means that sputtering is one option to deposit these layers, and it's also available to do this with industrial tools that feature very high throughput values. Now, looking a little bit into the passivation sequence here, we saw that hydrogen management is an essential part to achieve high efficiencies. There are multiple processes that affect the hydrogen incorporation and distribution. Of course, the passivation layers, they introduce hydrogen, but they also might serve as a diffusion barrier. And then during contact formation and post-anneal, you have the redistribution of hydrogen, and it's very essential to balance these processes carefully to achieve a good hydrogenation of the interfaces and also the bulk. And if you do so and have the high quality wafers, you can have very high lifetimes, like in this publication, 1/3 of a second. And hydrogenation is one key to achieve this, and it's also part of a patent that we hold. Looking at the passivation, we saw that UV degradation is currently a hot topic. There's a recent publication from ISE where we investigated cells from industrial producers and also observed some severe UV instabilities for the cells, meaning that these were investigated without any cover glass or encapsulant, but the cells themselves showed quite strong degradation. This is something that should be investigated in more detail and should be carefully monitored. Finally, LECO was a hot topic in this conference already, and we agree fully that this has been a breaking innovation in the TOPCon process. We at ISE were one of the first to apply this process to TOPCon cells, and it was game-changing because it decoupled the contact resistance from the contact recombination parameters because of the formation of these very small current-fired contacts. And the major part of the interface under the silver finger is still passivated by the passivation layers, and this gives a very high quality of the contact regarding very low recombination parameters. This has been implemented, and it strongly affected the whole process chain. For example, it enabled the use of aluminum-free pastes, much lower firing temperatures, and then in turn also very different boron diffusion parameters with a more shallow profile, which allowed lower diffusion temperatures, more cost-effective processes here, higher throughput, and also higher sheet resistance, increasing implied VOC values. So at Fraunhofer ISE, we have baseline technology for TOPCon, which is currently exhibiting 24.5% on M2 wafers, and we were recently able to upscale all tools to an M10 format and achieved 24% there, and we are looking forward to implement recent developments also in our baseline process, hoping to improve it further to keep up with industry standards. One challenge that we all face is silver consumption. And here one alternative that we promote is plating of copper contacts instead of silver, printing silver pastes. And we have a pilot fabrication at ISE together with our industry partner Arena, where we fabricate large area TOPCon cells with plated contacts. And we were able in the first batch to already achieve efficiencies that are similar to the screen printer reference. This is the cell that you saw on the slides before. And for these cells, we were able to demonstrate a very low silver consumption. And on the long term, we also are confident that plating cells would be able to be processed without any silver consumption. Another technology that I'd like to draw your attention to is the passivating edge technology, which was developed at Fraunhofer ISE. It's a very important technology for shingle cells, but also for half-cut cells, which are already mainstream. We know that if you cut cells into pieces, you introduce recombination at the edges, and the passivated edge technology that we developed allows to passivate these um, edges, as you see here. This might be a high throughput approach where you stack, in this case, shingle cells and passivate the interfaces, the edges here with an ALD aluminum oxide layer and subsequent annealing. And this is also an approach that is where we hold a German patent, and it's enables to recover most of the efficiency losses that are introduced by cutting the cells into stripes. Okay, so looking at another topic, what comes after TOPCon? It's topic of this conference also. Is there what are the emerging technologies? What we looked into in the past years is the TOPCon rear emitter concept, what we call a TOPCORE cell design. Here you see the conventional TOPCon structure, and compared to this, the TOPCORE structure switches from N-type to a P-type wafer, and it also omits the conductive front layer on the front side. And this gives some advantage in efficiencies, as we could demonstrate at that time with record efficiencies that time, due to the omitting the inherent recombination that is coupled to the presence of this highly conductive layer. I will share some details on this now. So here you see the recombination parameter of this front emitter versus the sheet resistance. And of course, if you increase the sheet resistance, you decrease the recombination parameter. And this is known that you can achieve very high implied VOC values when increasing sheet resistance that has been implemented in industry in the past years. But still, there is an intrinsic recombination, that is this gray line, which is Auger recombination linked to the doping itself that you cannot omit. And at current sheet resistance values, this still covers about 1.5 femtosecond per centimeter that is inherently present when you have a front doped layer. And this could be omitted by using the TOPCORE cell structure. Another topic for TOPCORE is switching to P-type wafers. It is known that P-type material is much more prone to metal contamination, so it's much more essential that you have a clean production, preventing contamination. On the other hand, we investigated industrial CZ materials that are already in the market, high resistivity CZ materials, which are suitable for TOPCon approaches and TOPCORE cells. And we achieved very high lifetimes here. So we think in principle, there's no limitation regarding P-type wafers to be able to provide also high efficiencies. Of course, these cell structures should feature local TOPCon structures on the front side. We were able to implement this on small area cells already. One challenge here is the alignment of the structures. Of course, you need very narrow local TOPCon fingers to minimize the parasitic absorption. And it's a question how this alignment requirement can be met by industrial production conditions. Finally, looking in the future, we also think that TOPCon-based cells are a very good choice for bottom cells in multi-junction or tandem devices. In principle, there are different options to use TOPCon cells as bottom cells. This is a straightforward approach that we call inverted TOPCon, where you just flip the current TOPCon structure and you have the N-type TOPCon layer on top, and you replace the silicon nitride layer by an ITO layer, and then you can process the top cell on this. It's very close to industry standard, but there are some challenges that we see, which is the hydrogenation of this interface, which is not straightforward if you don't have the nitride layer in place, and also finalizing the metallization before the top cell processing poses some challenges in our view. One alternative is the TOPCon square structure that we propose. It features full area N-type TOPCon on one side and P-type TOPCon on the other side, which allows a lean process flow. But also here we see some challenges like hydrogenation, and also the quality of P-type TOPCon on textured surfaces still lags behind a little bit compared to N-type TOPCon. We were able to implement the TOPCon square structure in multi-junction devices. In this case, it's a 3-5 silicon multi-junction cell
Andreas,
with a
can
TOPCon
you
square.
finish in a minute?
Yes, thanks.
Thanks.
So with this, we were able to demonstrate a 36.1 efficiency record cell, and this shows that TOPCon square is a good choice for a bottom cell. So this brings me to a summary. We saw that TOPCon was there for a long time, a shivering giant. We looked into industrial process details. I introduced copper plating, passivated etch technology developed at ISE, TOPCORE cell structure, and multi-junction cells. So let me thank you for your attention, German government for funding, and also our industry partners for their continued supply. Thank you. And I'm looking forward to your questions.
Thanks, Andreas. Unfortunately, we have very limited time, and I think some of the questions I will cover in the panel. Anyway, you will be in the panel. Meanwhile, there are some questions in the chat window. Please stay back, enjoy the conference while answering these questions.
Thank you.
Thank you.